So that violates the law of heat flow because heat cannot flow from a cooler object to a warmer one.
That's not what's going on. We're talking purely in radiation. We're not talking about convection. This is a radiative model.
About radiation too. Yes, I'm talking about radiation. I'm talking about heat flow in terms of radiation. Yeah. Heat
Cooler
cannot transfer
objects
from cold to hot
still radiate.
in radiative terms. Yes, and cold objects are physically cold to the touch, but they don't send heat to warmer objects.
They do radiate. If you
they do radiate, but radiation is not heat. Not all energy is heat. Just because
radiation
it radiates does not mean it is heat.
by the surface becomes heat because the surface absorbs and emits. So the radiation emitted by the atmosphere that reaches the surface.
Heat only comes from a warmer surface, from a warmer body. The atmosphere has no heat to send to the surface. The surface is warmer, so the atmosphere has no heat to send to the surface. The atmosphere, in fact, gains all its heat or most of its heat from the surface. There's probably some direct absorption from the sun, but the atmosphere gets all of its heat from the surface in the first place. So you can't recycle heat back to the surface to make the surface hotter still. It's a
You can, because there's an equilibrium.
Of the second law of thermodynamics.
You are taking energy from the surface, so the radiation from the surface, warms the atmosphere.
Yeah, and that's fine, but the atmosphere can't turn around and heat the surface.
It can because the atmosphere, if
the atmosphere is passive,
the atmosphere absorbs and emits radiation.
Familiarize yourself with the second law of thermodynamics, and this violates even the first law of thermodynamics, which indicates that heat flow is required to increase temperature. So what heat, if the atmosphere is colder, what heat does it have to send to the surface? Just because you draw that arrow in there, sure, that arrow indicates some energy, but energy is not always heat. Energy is not always heat, whether it's radiative energy or whatever type of energy. Energy is not always heat. Energy can only act as heat, and that means as a temperature forcing energy, as a temperature increasing energy, if it comes from a hotter body, and that's because it has additional...
that's not true.
Radiation. Well, you're just lying. I mean, go refer. Have you ever taken? I mean, what are your credentials here? Do you have any training in physics or astronomy? Because you really need to familiarize yourself with the basic thermodynamics text here. You can't just say that's not true. You can't just say that heat can flow from cold to hot. I mean, why would I accept you saying something like that to me?
Because we're not.
Do you understand how ridiculous that is?
We're talking about radiation. We're not talking about one hot object touching a cold object. That's not what we're talking about. We're talking about radiation balance.
Yes, of course. Yes,
and so the atmosphere radiates down to the surface, and the surface absorbs that radiation and re-emits it. And then
you're just making that up. You're just saying that.
That's true.
Just because you're saying that doesn't make it true. I'm referring to the laws of thermodynamics. The laws of thermodynamics say that heat can only flow from a warm object to a cold one. A cold one,
if they are in contact.
With radiation as well. It applies to radiation. The laws of heat flow are the same for radiation as they are for conductive transfer and diffusive transfer. There's no separate laws of thermodynamics for radiation.
There are
radiation that allow radiation.
Radiation does not require direct contact between two objects. The sun warms the earth, even though there's a vacuum between the sun and the earth. The atmosphere warms the surface partially through this radiation that is coming from the atmosphere back down to the surface.
That's not what any textbook of radiative heat flow in radiation says. There's no indication. Just look at the equation. The equation is radiative heat. Yeah, the equation is, here's the equation for radiative heat flow. It's similar to conductive heat flow. It's the hot temperature minus the cold temperature. So that shows that heat flows only one way from the hot object to the cool object. Just the same, it looks very similar to the equation for conduction and for diffusion. The only difference is there's a power of 4 for the radiative equations, but otherwise they're the same. Heat flows one way only.
That's not necessarily.
Yes, here they are, right here. Here's conductive heat transfer, and here's radiative heat transfer. Okay,
conductive, that's fine. The objects are in contact.
Yes, and here's radiative heat transfer.
I'm not familiar with that equation. Sorry.
Well, how can you not be familiar? This is a base. This is first year undergraduate stuff. So why are you here trying to tell me about first year undergraduate stuff that you don't know about? You don't even know what this radiative heat transfer equation is. This is the damn well most basic radiative heat transfer you can possibly think of. So like, what is this discussion supposed to be to me? You understand what I mean? You don't know. You don't know what this radiative heat transfer equation is. You've never seen it before. So, and you're trying to tell me about radiative heat transfer?
Yes.
Do you understand how ridiculous this is? Like, it's absurd. You're trying to educate me about radiative heat transfer. And then we show you the simplest possible equation. This equation actually would apply directly to figure 2.3 because it's a plane parallel system to which this equation would actually apply directly. And you say you've never seen it before and you're not familiar with it. So what are we supposed to do here? Hey?
The atmosphere.
You want to keep telling me? So you don't have even a first week undergraduate education in physics or thermodynamics. And I have a master's degree and I work for the Canadian Space Agency and I work with satellites in space. So how about I sit here and you frickin' tell me how radiative, why don't you just make up some new radiative transfer equations? Let's erase this one that someone posted here. Let's get rid of that because you're not going to like it because it shows heat flowing in only one direction from hot to cold. And once you educate me now.
Let's have this the other way around. So you're saying that the atmosphere cannot radiate towards the surface.
It cannot
because
send
it is colder. I'm asking a clarification. I'm not trying to
anything that radiates, obviously. First, okay. I want you to accept that not all radiation is heat. Not all energy is heat. Do you accept that? I mean, you probably wouldn't understand that because that comes probably in third year undergraduate thermodynamics. So you've probably never experienced or come across such a distinction before. Anyway, it's important.
Objects,
not all energy is heat. Not all energy behaves as heat.
I know that not all energy is heat. I know all objects radiate.
Heat is what is required to go back up to that very first equation. Heat is what is specifically required, or work. In this case, there's no work. We're only talking about heat. Heat is specifically what is required to increase temperature. Specifically.
And so the atmosphere has a temperature. So the atmosphere radiates. And so part of that radiation goes back down to the surface.
Yeah, but not as heat. It can't be as heat.
It can because the radiation from the atmosphere gets absorbed by the surface, and therefore it warms the surface.
You're looking at the radiative heat transfer equation right here, which is from basic thermodynamics textbooks, and radiative heat transfer. And you're contradicting, physics textbooks here. So you're going to say, despite someone has posted the radiative heat transfer equation, which shows that actually the cooler object is not going to send any positive heat to the warmer one. You say, well, yes, it is. So, I knew that this is where the conversation was going to go, and I knew that was going to be your position, and I knew you wouldn't care about being shown the actual heat transfer equation. I knew you wouldn't care, and you would just say, yes, it still does. So, what are we supposed to do here?
So the atmosphere, right, emits radiation.
Mm-hmm.
Yes. So the atmosphere has a temperature. It emits radiation. Is that okay?
Yeah.
Okay.
Well, sure. Go outside. Right now it's fall here. It's actually starting to snow here. So right now the atmosphere is emitting radiation outside my house, right? So how come when I go outside I don't feel the radiation from the atmosphere heating me, right? It's a pretty basic experiment to go do. You should be able to go feel the atmosphere heating you and increasing your temperature if it can transfer heat by radiation. So you said, no, it's not going to transfer heat by conduction because you go outside and then you're obviously going to conduct with that colder air and it's going to feel cold. But however, you're saying that the radiation should actually come back and do heating instead of the conductive cooling that's going on, except that's not actually what happens. You just get cold.
Well, I know what happens if I go outside. My body emits radiation. And so the atmosphere is also emitting radiation. But the radiation that is leaving my body is greater than the radiation that's coming to my body. So my body would cool. Correct.
Right. So you're heating the atmosphere. Right. So
yes.
So your body's going to cool. So you just so how do you turn that around then to say that the colder atmosphere is going to warm up the warmer surface? So put your body in place of the warmer surface.
Because my body hasn't reached the equilibrium temperature because my body is persistently emitting heat. So once my body
it doesn't matter if it's equilibrium or not.
Right, but once my body does reach the balance, my body will stop cooling.
Yeah, you'd be much colder.
Sorry?
Yeah, you'd be much colder, right?
Right. So
you'd be
I would cool.
Here.
Right, yeah, I'd probably get pretty cold. But once I do reach my equilibrium temperature, I will stop cooling, and we will have reached a balance, right? If I'm
Sure, that's
outside,
fine.
and that's what's going on in figure 2.3.
No, that's not what's going on. No, what's going on in figure 2.3 is it's trying to show that the surface becomes hotter from the radiation from the atmosphere. And that is what you were trying to argue previously as well, is that the surface becomes hotter from the radiation from the atmosphere.
Yes, and the surface reaches the equilibrium temperature.
Well, I know you say that, but that's contradicted right here from the radiative heat transfer equation. And it's contradicted because when you go outside, you don't actually experience that. And it's contradicted by real greenhouses, which should demonstrate that temperatures can be generated higher than which they're being heated up by sunlight, but they don't actually show those temperatures. They only show the temperature at which they're being heated by sunlight. There's no amplification of temperature from back radiation from the glass ceiling. That is simply not found. The temperatures are not generated that way.
You don't agree with the figure 2.3 because there is no way that the atmosphere could emit radiation down to the surface?
See, you're mincing words. You're mincing
I'm asking.
words.
I asked. Sorry.
Let me explain. Let me explain. Please be careful about your mincing of words and your definitions. The atmosphere can emit in all directions. Not all energy can act as heat. And the energy that the atmosphere emits, being a cooler body, cannot send heat back to the surface to make the surface warmer.
It can.
So it emits energy, but it does not transfer heat, because heat can only transfer from a warmer body to a cooler body. And right here is the radiative heat transfer equation, which directly applies to this situation in figure 2.3. And it shows that. And this is straight from a thermodynamics textbook, which you can go confirm for yourself. And then from the first equation that we looked at, the first law of thermodynamics, you specifically need heat in order to warm a body. Now, the radiative heat transfer equation shows that there's specifically not heat transferring from the atmosphere to the surface. And therefore, you have two laws of physics working together, which provide the answer. There's no other interpretation required. You have the two mathematical laws of physics, which show precisely what happens. So what does happen in figure 2.3 is that sunlight comes in, heats the surface, and then the high temperature surface, the temperature or the surface that's been induced to high temperature heating from incoming sunlight, then transfers that energy as heat then to the cooler atmosphere. And then the atmosphere becomes warmed up from being heated by the surface. And the surface transfers heat into the atmosphere by conduction and convection and by radiation as well.
Talk only about radiation. Because that's what's talking about in figure 2.3. We're not taking into account convection and conduction in figure 2.3.
I'm just saying it. Yes, well, I'm just saying.
I know in reality that's
obviously we have to acknowledge that's what happens, but sure, in figure 2.3 we can talk about the radiative component, and the radiative component is that the heat radiatively flows from the warmer surface, as per this equation at the bottom, from the warmer surface into the cooler atmosphere, and then keeps on flowing, and then the heat keeps on flowing down the gradients from there, which would be largely to outer space.
Okay. So the only issue you have is that I'm asking. The only issue you have.
I don't have any issues. I'm not talking about issues. I don't have issues. I mean, I'm using the laws of thermodynamics. I'm using the first law we looked at, the law of conservation of energy, and I'm looking at this radiative heat transfer law. So I mean, my issues are that I'm referring to standard textbook thermodynamics.
Okay, so so in your description just now, you are okay with the arrow down from the sun, you're okay with the arrow up from the surface, and you're okay with the arrow up from the atmosphere, right?
The arrow down from the atmosphere is fine, but it cannot be interpreted as heat flow from the atmosphere to the surface. That's the important distinction here.
Because you're saying that
because of the radiative heat transfer equation, because heat does not flow from cold to hot. Let me repeat. I mean, that was a great question. You finally asked me why, so let me just repeat that. Okay, not one. Here's a bullet points. Do I need to write this down? 1, not all energy is heat. 2, first law of thermodynamics, what is required to increase a temperature is heat. 3, radiative heat transfer equation, right here, shows that heat does not flow from a cold object to a warm object in radiation with radiation. So that's your answer. So that's the why. The bottom arrow.
It does affect the radiation budget, because the surface would have to be cooling less quickly. Because
cooling less quickly does not mean higher temperature. Cooling less quickly does not mean higher temperature, right? So cooling less quickly from where, right? It's the point of the interpretation in climate alarmism and in this radiative greenhouse effect. The specific thing is the interpretation of that downward arrow, and it is specifically interpreted as a source of energy that can induce higher temperature on the surface. That's specifically its function. So that downward arrow is specifically for inducing a higher temperature on the surface. That's specifically what it's for. So I refer to the first law of thermodynamics and the radiative heat transfer equation and simply say that interpretation is wrong. That downward arrow can exist, but not all energy is heat. And so it does not function as a temperature increasing function for the surface.
I've got a question.
Well, hold on.
No, let's get someone else in here. Who's got a question?
Okay, well, go ahead.
Yeah, I just want to ask this question. What stops that downward arrow from converting to whatever energy it is into heat energy later?
So that's a good question, and you get into that in fourth year undergraduate thermodynamics, and so you get into microstates, right? Microstates and macrostates and frequencies. So basically in frequency populations and oscillations. So you have atoms that are oscillating in a lattice and all sorts of stuff like that, right? So it's basically modeled as a system of springs, atoms basically on springs. And so these springs are all oscillating like crazy, right? And so they develop all these different frequencies. So how much energy do you dump in? I mean, this is all really advanced physics, fourth year physics, right? Fourth year thermodynamics. So you dump a whole energy into this lattice of springs that are holding these atoms together as your modeled surface. And what happens to it? How does that energy get spread out? Well, it gets spread out in all sorts of different ways. I mean, there's a whole history of thermodynamics of figuring out how this develops. You get the Maxwell-Boltzmann distribution in velocities and speeds, all sorts of stuff like that, right? Eventually, you get the Planck law, and you get the problem of quantization. So this is all how they had to figure out quantization, is explaining how this energy gets distributed in such a lattice.
Yeah, the electronic vibrational rotational modes. Yep.
Yeah, so they were trying to figure this all out, and back then everything was analog, and so but then they ran into these strange infinities and these runaway. It was called the ultraviolet catastrophe and things like that because they couldn't model it. And then Planck came up with the idea of the energy must be quantized, or what would happen if the energy was quantized. And then they saw that the equations suddenly started solving and making sense when they quantized the energy. So anyway, the basic idea is that a cool object is made up of a bunch of frequencies of oscillating atoms, and these atoms are oscillating at a whole bunch of different frequencies. But the general distribution, like sort of the histogram of the frequencies of all the energies involved, basically follows a basic function, right? So a cool object has lower frequencies. Basically, just think of it like that. A cooler object has low, slow frequencies. The atoms aren't moving very quickly. A hot object, the atoms are being jostled around very, very quickly, and so they have higher frequencies of oscillation, right? So the basic idea then is that the cooler object does not have the higher frequency population that the hotter object already has. The cooler object, and is basically like an information transfer. The cooler object does not have any information, which would be heat, to transfer into the hot object, because the hot object already has all the frequencies that the cool object has, plus a whole lot more, right? So the hot object has all of the frequencies that the cool object is vibrating at, plus it has its own at higher, and it has a much more population across all frequency ranges anyway. So the cold object simply does not have any higher frequencies to induce into a hot object. Whereas if you turn that around and you touch that hot object to the cold object, or think of it that way, this hot object is going to transfer all sorts of information into the cool object. All these higher frequencies that the hot object contains can be picked up by the atoms and molecules in the cool object. And then that's what heat transfer is. It's basically a transfer of energy, a transfer of information. All the information, which is these high frequency states that the hot object is vibrating at, can transfer into the cool object and speed up the cool object's internal vibrations.
That was very good. I agree with everything you've said about dipole radiation and the Planck function. Agree with everything.
Right, and then so that is the basic reason why heat, it's simply impossible for heat to transfer from cold to hot, because you're talking about a basic transfer of what would not be there. It's simply not there. That's what the additional heat that the hot object has, what it is physically, is these higher frequencies, and the cold object doesn't have that. So you're saying that the cold object would have to transfer what it simply doesn't have for it to be able to transfer heat to the warm object. So that's your basic second law and first law right there. And that's why cold does not send heat to hot. Even though a cold object can be radiating, the radiation that is emitted outward from the cold object, when it reaches the hot object is like, I already have all that. That's not new information to me. That's not telling me anything I don't already know, and I'm already populated with all those energies. So what there is instead is the hot object is going to send its radiation to the cold object, and the cold object is going to see this higher frequency radiation from the hot object, and so the cold object is going to be warmed up and heated up by that.
So okay, you without a doubt have taken definitely graduate level radiation courses. So when I take, so we're talking about, so we'll talk about the figure again. The loss, so we have to balance ingoing and outgoing for both the surface and the whole Earth, correct? So what's coming into the surface has to equal what's going out of the surface, right?
Well, generally, yes. But I mean, generally you don't have, the Earth isn't a static system. I mean, once you really get to the inside, what was done previously for the external emission temperature, that's an easy thing because it doesn't depend on anything that's happening internally. And so you just say, okay, the effective emission temperature of the Earth is 255 K or minus 18 C. That's no problem. Yep. But now internally, the system is not a nice static stable system. Over the long term, you can see there's energy balance, but every morning and every evening there's energy disbalance. Maybe at about 2 p.m., 3 p.m., there's a few brief moments of energy balance where the incoming solar is matched by the outgoing, but generally the system is almost always out of balance.
But we're not talking about the day-to-day variation in radiation. We're talking about the actual
physics that occurs. But that's the actual physics that occurs, right? The actual physics that occurs is actual real time, right? Like that is what actually is occurring. So if we try to make some model that's some smooth out average model, then what are you talking about now? Now it becomes, you know what I mean? Now you're not talking about something that's a reality anymore.
We are talking about the total budget.
Right, and the total, like I keep on saying, the total budget is fine for calculating the long-term external emission temperature of the Earth. Internally, though, it's a totally dynamic system that's not in thermal equilibrium at the surface, because the temperature changes every morning, every minute of the day. It's never stable. So because the temperature is constantly changing, that shows that the system is simply not a static system. Plus, you really have to take account of what is the effect of real-time solar input. So real-time solar input is quite warm. It can typically be 1,000 or more watts per meter squared. Yep. With that sort of input can generate like cumulonimbus clouds where you literally raise lakes into the sky to 40,000 feet. Like that's how intense. That's how intense that energy is. It's ridiculously intense, right?
Yes.
Yeah. So, but then on the other hand, making this smoothed out model where we say that the input energy is S0 over 4 times the albedo, which is equivalent to minus 18 C, saying that that's the input. right? That was fine for calculating the output, right? Again, S0 over 4 times the albedo. That's fine for calculating the output and saying that this is the output energy and this is the output temperature, and that's fine. But what happens here is that that exact same expression is turned around as the input. Now we're saying that the input is 255 K, right? Or minus 18 degrees Celsius. So if the solar input was minus 18 degrees Celsius, does this represent anything that is happening on the ground at any time, anywhere? I mean, I think it's at like 75 degrees north latitude. That's where you got to go to find that sort of a solar input. For the whole rest of the planet, inside plus or minus 75 degrees latitude, you have the sun generating all sorts of insane physics that minus 18C would never, ever be able to do. Minus 18C cannot raise a lake to 40,000 feet altitude. Minus 18C can't do that.
Yeah, no, that's understandable because there's a large amount of day-to-day and intraseasonal variation in the incoming solar radiation at a particular location, right?
And that's what becomes important. I mean, that's what becomes important. That's what the climate system is. The climate system can't be smoothed out internally to this type of thing. Or if you are going to smooth it out to something like that, then you have to here. How do you attach a picture? So here's something that's a bit more reasonable to consider for a model.
So can I ask, I want to ask one final question for figure 2.3. Mm-hmm. Does the radiation budget for the surface have to be balanced? Because I would say yes. The ingoing of the surface and the outgoing of the surface have to equal, so the surface is at a, you know, as a total temperature that is appropriate. That is fixed.
I would say you're not. I would say you're not talking about something that exists in reality anymore, because that never happens on the surface. The surface is constantly changing temperature, morning, day, and night, which means that
we're talking about the total of the surface.
The total surface radiation balance.
The total surface budget. Is that balanced?
Right. Yeah. Over the long term, yeah, sure. Over the long term, sure. I mean, obviously, the temperature of the Earth slowly changes up and down, right? So, I mean, there's some sort of a little imbalance, but in general, there's a long-term balance aside from the day-to-day variations.
And we're not talking about the day-to-day location-to-location variation in figure 2.3. We're talking about the total. So the total surface budget should have a balance of ingoing and outgoing, correct?
Mm-hmm. Yeah.
Yeah. So to balance that surface budget and to have the total system budget be equal, you need to have the atmosphere, the surface absorbing atmospheric radiation.
Yeah, but you have to apply heat flow. No, you have to abide by heat flow. You can't just do it by a basic conservation of energy and think that you can add cold energy to warm energy like that. That's too simplistic, and it's physically incomplete. It's simply incomplete in the realm of physics, because you have to start referring to heat flow and the behavior of what heat is going to do. So you can't just you can't just turn around and invent this downward arrow from the atmosphere and just now start interpreting that as heat, when that's a physical impossibility, and when heat flow is actually only the other way, from the object with the higher frequencies to the object with the lower frequencies. Right. So you can't do that. Now, the reason why it is set up that way in these diagrams is because of this error of using minus 18C solar input. So when you think, gee, the solar input is only minus 18 degrees Celsius, that's really cold. How do we come up with a higher temperature? And then you say, oh, I know. Let's say that the atmosphere, even though it's colder than the surface, heats the surface some more. And then that's their answer. And then that's how their climate alarmism works. But it's all based on this false premise of, you know what, that minus 18C input of S0 over 4, that's actually only for the output. You cannot turn that around and claim and say that that is the same thing as the input, because the frequencies are totally different. First of all, the S0 over 4 times the albedo as the output, those are low frequencies, long wave, that's a long wave output. So to turn that around and say that's equivalent to the input and can be used for the input, the frequencies are all wrong, because the frequencies of solar are visible. They're short wavelength, right?
Yep.
They're high frequency. So so there's a big error right in the beginning of that. And then, of course, as I said, the whole scheme here is to come up with a way to warm the surface, thinking that the sun can't heat the surface. They literally think that the sun can't heat the surface and does not heat the surface, and that in fact in the atmosphere
the sun is heating the surface.
Yeah, to only
in the model. In our total budget, the sun heats the surface. So
at only minus 18 degrees Celsius. At only minus 18 degrees Celsius, and hence without any of the physics that the sun actually does. So without any physics that the sun actually does, the sun heats the surface at only minus 18 degrees Celsius. Yeah, sure, that is exactly what they're depicting. And then they say that the atmosphere must make up for the rest of the temperature by somehow sending heat to the surface some more, even though it's colder. So the whole system, right from the beginning, is based on illogical principles. So and that's why it doesn't work out. Yeah.
If we're talking about the radiation budget for figure 2.3, the down arrow.
It's not sufficient to only talk about a radiation budget and interpret all radiation as a temperature increasing function or potential or ability, because not all energy has the potential to increase energy or to increase temperature. Energy specifically has to come from a hotter body, which means that that energy has higher frequency components. And it's those higher frequencies that are needed to increase the temperature of another body, right?
Yeah.
So let's go down, and once you expand this budget that I posted here.
I don't want to talk about your figure. It's not what I'm here for. But I want to ask that.
Well, so I'm not here to talk to hear you wishing that you could violate the laws of physics. I mean, I'm trying to educate you and show you a more reasonable model, so you don't have to believe that solar input is minus 18C and that a cold object can heat a warmer object. I mean, why do you want to keep believing in things like that?
Well, I want to understand what they're doing when they're making this figure then, because the input needs to equal the output for the surface, and the input needs to equal the output for the atmosphere as well, correct?
That's far too simplistic of a situation. You need to put it in terms of heat flow. You need to use this heat flow equation to figure out how heat is flowing, and that's going to tell you what physics is going to occur. But I would say you can't really do that.
So would you agree
you have to go at a model like this one that I've posted down here and look at it in those terms.
I want to ask you, so would you agree with 2.3 if the down pointing arrow from the atmosphere weren't there? Is that satisfactory?
I think you seem to have forgotten something here that's important. So,
because what you're saying,
let me ask you a question. I want to see if you've picked up on anything yet. Is all energy heat?
No.
Thank you. So that downward arrow from the atmosphere is not heat, although
but it is radiation.
Right, but not all radiation as energy is heat. Although in this diagram,
but if the surface absorbs,
it is interpreted as heat. It does not absorb it because it's lower frequency.
You can still absorb lower frequency radiation.
But it does not increase your temperature. I mean, I don't want to say why you want to say that. Well, you're just making that up. I mean, you're just saying that. You're violating the laws of physics and the law of heat flow. First law of thermodynamics, what specifically is required to increase temperature? Heat. Says it very clearly, right? You even brought that equation up, so thank you for bringing that up.
But
let's go over that again.
That's when
First
the heat
law of thermodynamics.
To heat, you have to have it higher energy in than energy out.
No, you need heat in. You need heat, not just energy. You need heat. First law of thermodynamics. Specifically, heat. So what is heat? What form does it take on in physics? It's shown right here in this equation for Q, for radiative transfer. That was posted at 6:45. That is specifically the form of the equation for heat in terms of radiation. And it shows that heat does not flow from the cool object to the warm one, but of course from the warm one to the cool one. Of course, it's for the exact same reasons about transferring of frequencies and information.
So where we disagree is that the surface, so I'm saying that the surface does absorb from the atmosphere, and that's your point of contention, is that the surface does not absorb the emitted radiation from the atmosphere.
Not as heat. Not as a temperature, not as in any way that can increase temperature. Not as heat, which is of course what we're talking about.
Wait, can you ask that question again? I missed it.
But my question?
Yes, please.
So I was just trying to. So what I'm saying is that the atmosphere emits radiation, and the surface absorbs that radiation. And what you're saying is that that can't be the case.
It can't be the case that the radiation from the atmosphere acts as heat for the surface.
Okay.
And heat specifically is what is required to increase temperature, as per the first law of thermodynamics. And the form of the equation for heat in terms of radiation was given to us at 645. Radiative heat transfer.
Great. I think I'm good. I have to cook dinner, so
Hey, I would like to thank you for this. Like this whole conversation, this was awesome. I think we all are better off because this conversation happened, and I'm glad.
Well, if anyone wants to stay, I'd be happy to discuss this thermodynamic energy budget that I've posted here a few minutes ago, because this really shows a much more detailed and much more physically complete model than compared to this figure 2.3 up here, which violates the laws of physics and heat flow. My model does not violate the laws of heat flow. So who wants to go over it? Anybody?
I just want to say thanks for chatting with me.
JP, I wanted to ask one more question as a follow-up of energy transfer.
Yes. Mm-hmm.
So you said that heat can only transfer to a colder object.
Yeah.
As in, like, heat or that type of energy, the thermal energy can only transfer.
Yeah.
But, what if I rub two cold objects together and it becomes hot due to friction? How does that work?
Well, that's fiction. That's work, actually. Remember equation 1 up here for the law of thermodynamics, the first law of thermodynamics? So one of the terms is work. So heat is one term. You're not doing anything about heat in that case. What you're doing is work. You're doing work on the object. So by rubbing by using friction, you're putting work into that object via friction. So you're literally rubbing the lattices, like the molecular lattices together. You're rubbing them together, making them bounce off each other, rub against each other. And eventually you just build up energy that way. Like it just absorbs the energy from your muscles. The source of the energy is obviously your muscles and a few you ate earlier. So.
Right.
Yeah, so that's work. So that's basically would be considered work input causing a temperature increase.
So what would the energies that isn't heat be reflected back from the atmosphere? Like light?
It probably just resonates. It just resonates. Like standing waves, right? You've ever done that with water, right? Just standing waves just resonates back and forth. Doesn't do anything. And of course, light is bosonic, right? So light can just pass through each other, pass through itself without effect. Like it's what do you call it? Superposition, right? It just goes through itself with superposition. The underlying frequencies don't change and they just pass through each other. And frequency is the really most important thing when it comes to temperature. Temperature is basically a measure of frequency. So a higher temperature body has higher frequencies inside the motion of its molecules. They're vibrating at higher frequency. Cooler object is vibrating at lower frequency, right? So with light, light just passes through each other, through itself, photons, because it's just waves of energy, and they can superimpose on top of each other. But even though they superimpose, the underlying frequency components of each photon do not change. They remain the same. And so because superposition doesn't cause a change in frequency, then it doesn't cause a change in temperature either. So that's how the photons from the atmosphere can come down to the surface, but they don't induce a higher temperature because they're just superimposing. They're superimposing, but without a change in their underlying frequency.
I told you, the greenhouse effect does not exist. It's all a scam.
You want to go over this Earth's thermodynamic energy budget just quickly? I won't take your time. I won't spend a lot of time on it. We can just really quick take 1 minute.
Okay.
So anyway, click on it, expand it so you can see it big. So anyway, so we have the top of atmosphere solar flux coming in. So that's your 1370, which we calculated earlier. And it actually comes in, it's 121 degrees Celsius. That's how high of temperature can actually induce when you're in orbit. It's hot as hell. That's why
I believe that.
or white spacesuits. Yeah. So when this gets down to the surface around the equator, it's still almost 88 degrees Celsius. That's what generates our main climate. Like 98% of our climate is the cells. I think it's called the Hadley cell, I think, is generated just from that 90% region, getting all that nice hot energy, generating all that evaporation off of the oceans, and the oceans actually absorb. The oceans have an albedo actually almost near zero. So the oceans actually absorb higher than the equivalent of 88 degrees Celsius. They absorb almost everything that the sun puts into it. So quite a bit of energy. So that generates most of the climate. Anyway, if you just look at the external text here, you still get to the minus 18C output, but we never turn around and use that minus 18C output of the Earth, that 255K output of the Earth. We never turn around and use that as the input. You would never do that. We keep the input as this hot, high temperature, high power, high frequency input. We keep that there. And then we recognize that, wow, the climate is created directly by the sun. Whereas in that earlier figure, what was it, 2.3? And if you look at their actual budgets and their actual literature who actually use this, their numbers are literally that the atmosphere heats the surface at twice the power of the sun. They literally have that in their freaking literature, that the atmosphere provides twice the amount of heating power than the sun does. And they have to do that because they use this output for the input, this S0/4, this minus 18C output, which should be output. They use that as the input. So I wrote to them, to the American Meteorological Society. I wrote a paper for them saying, you can't do that in physics. It doesn't make sense. And here's the basic laws, basically the discussion I just had. And so I have this on my YouTube video, which I posted somewhere. I should post it for you guys. Or Boomy, if you want to quickly pull that up and just post it, maybe then people could find it if you want. But anyway, I had two peer reviewers. The one reviewer was like, wow, you know what? That is exactly what I teach in my classes, and I had all sorts of references showing this is what you guys are teaching in classes. And so the one peer reviewer was like, yeah, that is what I teach in my class. And you know what? That doesn't make sense to say that about the sun. They're like, you're right. You have a really good model here. And he says, I recommend this for publication. The other reviewer was like the guy I was just talking to. And he's like, no, he's like, the existing literature says that the sun does not heat the earth. And therefore, because that's the existing literature, I do not recommend your paper for publication. So just because you can show with math and with physics and by standing outside that the sun heats the earth, the existing paradigm is that we believe that the sun does not heat the earth, rather the atmosphere heats the earth. And therefore, and he was really nasty about it too. And so he wrote to the editor and said, don't publish this guy's work, it's all quackery. So you have two peer reviewers saying completely opposite things, right? One saying the sun doesn't heat the earth and don't publish that because the existing literature that we're all working from is based on the sun not heating the earth, and that's the basis of climate alarmism, right? So it's really quite absurd. Watch this video. Boomy just posted it up here. You should watch it. It's absurd. That's what's happening. That's what's happening in climate science.
All right. That was awesome.